Welcome back to today's Explainer. Today, we're diving into Complete Lesson 2.5, where we're going to completely demystify the fundamental building blocks of the universe and turn the sometimes intimidating periodic table into a beautifully organized map. Seriously, whether you're holding a smartphone, drinking a glass of water, or just taking a deep breath of air, absolutely everything around you is made of the exact same basic ingredients. And today, we're going to figure out exactly what those ingredients are.
So picture this. Over 2,000 years ago, a Greek philosopher named Democritus posed this exact thought experiment, and honestly, it's the perfect place for us to start. Imagine taking a piece of material and cutting it in half, over and over again. Can you just keep slicing it into smaller and smaller pieces forever? Or do you eventually hit a physical limit? What actually remains? Well, this simple question is what gave birth to all of modern chemistry.
All right, here is our roadmap for today. We're doing a full zoom-in, zoom-out approach, starting with the invisible building blocks, moving to nature's pure ingredients, seeing how atoms actually join together, mapping the universe, and wrapping up with the secret code of chemical symbols. Let's get to it. Part 1. The invisible building blocks. To begin our journey, we are going to zoom all the way down to a scale that is literally invisible to the human eye.
Back to that thought experiment. Democritus hypothesized that eventually you'd hit a wall. You'd reach a piece so incredibly small it just could not be cut up anymore. He called this tiny piece of matter an atom, which literally meant cannot be divided in his language. Now, for centuries, this was just a wild, mysterious theory. People couldn't see anything that small, so they basically just had to trust this grand idea that all matter was made up of these impossibly tiny specks. But today, we don't have to just guess. Using incredibly powerful modern tools called scanning tunneling microscopes, scientists can actually see these structures. Those little bumps you're looking at, those are individual carbon atoms forming carbon nanotubes. The word nano meaning very, very small. It's absolutely mind-blowing that we can now literally photograph the fundamental pixels of our universe.
Moving right along to Part 2, Elements, Nature's Pure Ingredients. So what happens when you gather a whole bunch of the exact same kind of atom together in one place?
Well, scientists have discovered a total of 118 different kinds of atoms. And when a substance is made entirely out of just one single kind of atom, we call that substance an element. So out there in the real world and in our science labs, we know of exactly 118 different elements in total. Carbon, gold, and silver, those are all perfect examples of elements.
But here's the real kicker. Out of those 118 different kinds of atoms, only 94 occur naturally in the universe. The other 24 actually have to be synthesized, or basically cooked up by humans in a laboratory. Just think about that for a second. Only 94 naturally occurring elements. That is a surprisingly small alphabet of ingredients, yet when combined in different ways, they make up absolutely everything we see, touch, and experience.
To put that into perspective, let's see how this builds a physical object in the real world. Take a look at these beautiful, pure silver rings. Because they're pure silver, they are made of just one element. If you had microscopic vision and zoomed way, way in to see the atoms making up those rings, they would form a neat, tightly packed, repeating grid of completely identical silver atoms. And since every type of atom has its own unique properties, this silver looks and behaves totally differently than, say, pure gold or pure carbon.
All right, Part 3, how atoms join together. Because not all atoms like being tightly packed like that silver, let's explore their social lives a bit.
Turns out, some atoms are total loners. In 6 elements, like the gas neon, the atoms move around completely freely. They aren't attached to one another at all. They just kind of bounce around independently, keeping entirely to themselves. On the flip side, some elements are what I like to call buddy atoms. They naturally join together to form small particles. Take oxygen, for example. The oxygen you are breathing right now isn't floating around as single, lonely atoms. It pairs up tightly 2 by 2 to form a single oxygen particle. And then you've got the party atoms. Sulfur is a great example here. It creates a significantly larger particle made from 8 distinct sulfur atoms that link together to form this fascinating ring structure. It's still a pure element because every single atom in there is sulfur, but they definitely prefer to travel in this larger pack. Which brings us to Part 4, Mapping the Universe. Let's zoom back out from the microscopic level and figure out how humans actually make sense of all these pure ingredients.
Enter the periodic table. You've definitely seen it, but scientists developed this incredibly useful way of organizing all 118 known elements. It acts as the ultimate map of the universe's ingredients. They arrange the atoms systematically, so their mass actually increases as you read across from left to right. So hydrogen is the lightest, then helium, then lithium, and so on. But it's also brilliantly color-coded to group similar properties together, placing all the elements that act as metals together in one block, totally separate from the non-metals.
To read this map like a pro, you only really need to remember two simple terms. The horizontal rows running left to right, those are called periods. The vertical columns running up and down, those are groups. By placing elements into these specific periods and groups, scientists instantly know a ton about how an element behaves just by seeing where it lives on the map. It's kind of like a cheat code for chemistry.
Finally, Part 5, the secret code of symbols. Because let's be honest, writing out aluminium or phosphorus every single time you need a chemical formula would get exhausting real fast.
So, scientists developed a universal shorthand. Every single element is assigned a chemical symbol, which basically acts as a quick nickname. And there are strict rules for this code. Rule 1. The first letter is always an uppercase letter. Rule 2. If the symbol has a second letter, it absolutely must be lowercase. And Rule 3. While many symbols come directly from the English name of the element, some of them are actually borrowed from ancient languages, like Old Latin.
You can see how this plays out right here. A lot of symbols are incredibly obvious. Aluminum is simply Al. Oxygen is just O. Helium is He. But then we hit these awesome historical Easter eggs. Look at sodium. Its symbol is Na. Why? Because it comes from the Old Latin name for sodium, which was natrium. Same with iron, which is Fe for ferrum. It's this fantastic blend of modern science and ancient history.
Connecting all of this shorthand back to the real world, we can see exactly what these pure elements look like in the lab, sitting right next to the very symbols scientists use to study them. We've got solid metals like zinc as Zn, lead as Pb, that classic reddish copper as Cu, and iron as Fe. We even have bromine labeled Br, which is wild because it actually sits as a deep red liquid at room temperature.
And that wraps up our coverage of Complete Lesson 2.5. We've seen how absolutely everything starts with those indivisible tiny blocks and how we map them out on the periodic table. But I want to leave you with an incredibly exciting question to ponder. If these 94 naturally occurring pure elements are simply the letters of the universe's alphabet, what kinds of massive, complex, and beautiful things can we build when these different ingredients finally start bonding together to spell out actual chemical words? Something to think about. Thanks for hanging out with me on today's Explainer, and I'll see you next time.